Hello everyone, this is my first video and we're going to start by solving this question right here. I know most of you have seen this question in class and you probably wonder how to solve it. Or you didn't really understand what the lecturer was saying at the time. That's what I'm going to start with. I'm going to start with how to solve an ideal op-amp like the one before. So this is an ideal op-amp, and from the title, you know that an ideal op-amp has got it has particular conditions to it. So for example, the current between these two nodes is 0. So I plus I minus is 0. So this is the first condition for ideal op-amps. And the second condition is V plus is equals to V minus is equals to 0. So these conditions are now what define ideal op-amps. So to solve this question, since we have no resistor between these two junctions here, it means that there is no voltage drop across. So the voltage here is the voltage here, which is V minus. Now, if you were to do KCL along this node, you would end up with current that goes into this node right here, and the current that goes out of this node, like that. So the current that goes into this node and the current that goes out of this node, let's call this current that goes in to be I1 and the current that goes out to be I2. So you know that the KCL equations stand for the current that goes into the junction. If you had a wire like that with multiple circuits that go out like that, you know that the current in to a junction is the same as the current that goes out of the junction. So if you are to apply KCL to this question, right, to this node right here, you'd say I1 is equals to I2 plus I3 plus I4. So that is technically how KCL works. So back to the question. In this question here, the equation would be rather simple. It would be I1 is equals to I2. Now, we know that current is the change in voltage over the resistance. So if you had to write I1, it would be change in voltage from V in to V minus all over Rin. So it would be V in minus V minus all over Rin. So that is the change in voltage over the resistor. Now, if you had to write I2, I2 would be V minus minus V out, which is the voltage at the out, which is the voltage at the end, divided by the resistor. This is RF. So there are different types of resistors that you could find in this kind of question. You could find a capacitor, which its resistance is 1 over SC. You could also find an inductor, which is the capacitor is going to be SL, or you could even find just a standard resistor like you have here, or it could be resistance in series or in parallel. But the general term for the resistance you can use is Rin and RF, where Rin could be whatever the resistances that you have, simplified to be just one variable for simple solutions. So in this question here, if it's I1 is equals to I2, let's replace I1 and I2 in this equation right there. In this equation, so I1 is going to be V in minus V minus all over R in is equals to V minus minus V out all over RF. So from this condition here, you can see that V plus is equals to V minus, and in this particular question, V plus is equals to ground, which is 0. So let's continue this question right here. So if that's the case, then V minus is equals to 0, then it's going to be V in minus 0 all over R in is the same as 0 minus V out divided by RF. So simplifying this question is just going to be V in all over R in is equals to minus V out all over RF. So let's multiply both sides by RF. So the main reason why we're doing this step is because we know that voltage gain is the same as V out, output voltage, divided by input voltage. So input voltage, this is just V in generally, and this is just output. So if you're getting output over input, then what's this going to do? So if you divide everywhere by RF, this is going to be V in times RF divided by R in is equals to minus V out. Now let's multiply both sides by 1 over V in so that you can get it in terms of V out over V in. So these two are going to cancel out, so this is going to be RF divided by R in is equals to minus V out all over V in, and the minus sign can go on this side. So AV, or voltage gain, which is output voltage divided by input voltage, is going to be minus RF divided by R in. So this is the answer to the question that we've seen here. And you could, for all inverting amplifiers which are similar to this one, you could replace RF with either a capacitor, with an inductor, you could replace it with just a standard resistor or a series of resistances, and by doing that you could either turn this standard inverting amplifier into either a high pass filter or a low pass filter, depending on which resistances it is. So as you can see, R in is at the bottom. So from the equation you could see that the gain is going to be minus RF all over R in. So if you replace R in with a capacitor, for example, if this is a capacitor, the resistance of a capacitor is 1 on SC. So if you have to replace 1 on SC here, so it's going to be RSC minus RSC. This is equals to gain, because this is gain right here. So it means that if S, or which S is J omega, the higher the oscillation frequency omega, the higher the total value. So this would end up being a high pass filter. So it would clip all lower frequencies but boost all higher frequencies. But then if you have to replace the capacitor here, then what's that going to do? Is going to turn this one into a low pass filter, because it's going to be RF on SC. So what this means is that if there is high oscillation frequency, then the general value of amplification is going to be low. So this turns it into a low pass filter. So that's one of the applications that you can use a standard inverting amplifier for. And next video I'm going to show you how to do an inverting amplifier, And if you have any other questions, just leave it in the comments below. Thank you.